All right, ladies and gentlemen, mechanisms in chapter 18, carboxylic acid derivatives. I started with a review mechanism here so we could make a derivative of a carboxylic acid. This is a Fischer esterification. Fischer esterification. Lab students were doing this yesterday. Okay. First step is to activate the carbonyl. This time we're using hot, strong acid. Second step is to attack the carbonyl that you activated with the poor nucleophile. And when you did that first step, you made OTS negative, I hope you realize. Let's do it in black arrows, blue. And in your third step, you're going to make an oxonium in step 2, right? This is going to have a third bond to O. What do you do with your oxoniums very often in this course? Deprotonate, get your catalyst back. We'll do that in purple. I think I can get away for arrows not to cross here, but be careful in navigation here. And there you go. So you have right now the species here. Ding, 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 ding. Got the carbonyl back, old carbonyl there. Still have an OH. Is that right? What do we have? No, we don't have an OH. Here we do. We don't have a carbonyl anymore. Sorry, got to do a quick assessment here. We have an OH there, don't we? Hello. And we have the OH from before. And the new guy is OET. ET. So I'd like to remind you that this part needs to go. Everything black needs to go. What do you call that? Got an O and two H's. H2O. That's called the dehydration step, isn't it? And you need a catalyst that takes a proton off one spot, provides a proton for the other. OTS minus is our guy to take a proton. Not a very good guy for that. But before it can do that, this thing needs to be, I should use that word activated more often. I'm protonating the O. I'm activating it to be a better leaving group. I think in the future, I'm going to say that starting in chapter 10 in 241. Get that word activation in earlier. So I activated it. It's now going to be a better leaving group. OTS minus. Don't forget this minus. I didn't have it on there. I just put it on there now. It's going to grab that H in step 2, now that you got a really good leaving group. And it's going to leave. You have made an ester. Good job. Ready for a chapter 19 preview? Wow. Yeah, it's also on your test, so mandatory preview. pKa equals 10. Why? I thought alpha to a carbonyl was 20. It was. What's special about that H? What's special about that H? Alpha to 2 carbonyls. They both have a resonance stabilization effect. You can draw 3 resonance forms for the anion, not just 2. So yeah. Oh, I think I just gave away what happens in step 1. Hello? What's OH minus? Base. All right. Just do an acid base and then talk to me about what you think is next. You can't combine this. You just got to do step one and done. Draw me the result. Carbonyl, anion. Oh, yeah. If you're like me and you made a carbon anion, you get excited because you want to do synthesis when you do that. And look at this. Isn't this a new bond right here? Right there? Yeah. That red bond. It's a synthesis bond. You guys can tell me what to do. You've never seen this before. You've got to be able to tell me how to do this with 2 arrows. 2 arrows, and you can give me an answer with 3 symbols in it. 2 of the symbols are letters from the traditional alphabet, and one's a number. Nucleophile, primary carbon with a leaving group. That's what I wanted to hear. SN2. Nucleophile attacks carbon with leaving group. Carbon with leaving group leaves. End of story. Nice. The preview is for the acetoacetic ester synthesis. If you want a title to go looking for in chapter 19. 4. Preview 4. Chapter 19. FOR. Acetoacetic ester synthesis, which we'll be using in our retrosynthetic analysis most likely, or a similar synthesis called the malonic ester synthesis. And now we're going to do a new reaction mixed in with an old reaction. And I'm going to tell you, when you see this combination, KOHAQ, I usually reserve that for what's called saponification. Saponification. Saponification is easy to remember if you can embrace a little dyslexic nature. Move the O to there, and what are the first 4 letters? It's a word we use every day. Soap. Yes. Now, if you're using saponification with an ester found in nature, like those found in triglycerides, where there's 3 esters in 1 molecule, and triglycerides are made from what 4 pieces? 3, say it. Yes. Long chain carboxylic acids, we have a name for those. Long chain carboxylic acids, we have a name for those. Carboxylic acids found in nature with very long chains, 12, 14, 16, 18, 20, 22, 24, never an odd number either, for reasons you'll learn when we do test 4. That's what I wanted to hear. Fatty acids, 3 of those, each one made into an ester with the other thing you said, glycerol or glycerin. They are the same molecule. Glycerol and glycerin are 1,2,3 propane triol. 3 carbons in a row, each one's an alcohol. 3 alcohols. Triglyceride. 3 esters with 3 fatty acids. So when you use that molecule in a saponification, that's when you are really making soap. That's what it got named after. You're making 3 different molecules of soap. The 3 fatty acids become fatty acid carboxylates, conjugate base of fatty acid. Soap. Nice for washing. This one's not going to be a real soap, but the reaction is the same. OH minus is what's going on, right? So just reminder, step one, OH minus. Any takers on what you think OH minus is going to do if it's not going to be a base? Nucleophile, nice job. What do you think we should attack? Based on the structure of the product here, what goes away? The side chain that starts with a carbonyl. What do you want to attack? The carbonyl. What do you think happens in step two? Take a wild guess. It's a theme for chapter 18. Come back, leaving group bye-bye. And we're gonna go with a new color. Just a reaction arrow, so it doesn't have to be that clear. What do you got? We got a phenyl, acetyl group. That's an acetyl, isn't it? And now we got a carbonyl that has an OH on it. And a base. Ethoxide is a strong base, and an acid here with a pKa of 5. You got to agree, right? Normally, I don't like this leaving group, but in a reaction that already started with a molecule that wasn't a good leaving group, you are allowed to have molecules like it that are not good leaving groups because they existed from the beginning. But you can't stop here. The laws of pKa cannot stop in time because you want them to. You've got to protonate this and go away from a pKa of 5 towards a pKa of 16 here. I know you wanted to say 17, but it's ethanol. All right. Phenyl, carbonyl, carbonyl. You got your soap. That would be a decent soap. It's not natural, but it's got an anion, which makes it water soluble, and it's got a lot of carbons that makes it water insoluble, grease soluble. Grease is non-polar. Yep, it becomes ethanol. Step one, side product is ethanol. This is this. This becomes this, which is this. Are we clear? No. Should I pause?
Why didn't we make it 5 when we attacked?
Octet violation? Okay. She asked why we didn't come in and make a pi bond. I see what she was trying to generalize over here, I think. Yeah, we made CO2 minus and it's over. Step one is over. Step two, we're going to do, what do you think HCl is going to do with that thing first? Protonate, that's right, HCl, strong acid. We're almost done. Phenyl, acetyl. Oh, I'm going to redraw it. I apologize. Just for this reason, got the blue O here with the black H. Carbonyl. I just did a sigma rotation. And I'm tidying up because I want it to look real nice this next part. There. I got a hint for you. What functional group is beta to the ketone? What functional group is beta to the ketone? No, that is not an alcohol on the beta carbon. Carboxylic acid that is beta to a ketone, amide, ester, any carbonyl containing compound. This is not new. It's called Monday. So I'm linking with a reaction we already know now. What do you get when you heat this? Thank you. She said decarboxylation. And the mechanism from Monday is this one. Pi grabs H. Sigma resonates. And you generate an enol. My alpha's in the way. This doesn't, I don't like it. But I think you see the enol, don't you? I can make my alpha tiny. There you go. Now my beta's out of spot. And you get an enol. You're not done if you have an enol. There's a double bond here, and an O and an H. And, well, did you also make CO2 when you did that thing? The beta carbon. You want to put a beta on it, just so you're doing some bookkeeping here? Yeah. So what do we have so far? Saponification, HCl reaction. I'm gonna call first one was saponification. There's a quote. And then I'm gonna call this one acidification. And this is the first step of decarboxylation. I mean, come on. That is one righteous rap song, isn't it? Saponification, acidification, decarboxylation. Come on. Doesn't get better than that. Let's finish our decarboxylation. What's got to happen to go from here to here? I have what functional group here? What functional group? Enol. What do enols love to do? Most of them. It is about the 10th one we've seen. That's not a lie. You're moving an H and the position of a pi bond. There's a name for that. Tautomerization. Now look at the chemicals present, because whenever you do tautomerization, there are three scenarios. 1, acid catalyzed. 2, base catalyzed. 3, with intermol, we did last time. No acid or base. But you can't use that one here because step 2 has what present? Step 2 has what present? It's right at the top of the screen. Strong acid, you better have this acid catalyzed. And don't panic, the mechanism is the same whether it's acid or base catalyzed. You need an acid-base conjugate pair. And Cl minus grabs the H, pi happens from the sigma, the old pi protonates, you are done. Tautomerization in our new righteous rap song. So at the end of your acetoacetic ester synthesis, you do a saponification, acidification, decarboxylation, and all of that gets rid of what? The whole ester functionality is gone, right? Whatever R group was attached is just gone. So why do we do this? To make a molecule get rid of stuff. We don't usually do that. Get rid of stuff in a molecule. We needed this. pKa 10 means not terribly weak. Easily taken off with a cheap, strong base. You can't do that if there's only one carbonyl present. You got to use expensive, dangerous bases. Because the pK is 20. If there's only one carbonyl present, the pK is 20. Half the class didn't know that last test. You get another chance this test and another chance the next test. Alpha to a ketone is 20. Alpha to 2 carbonyls. That's new. Please, don't wait for the second chance on this one. It will be showing up on this next test. What's your pKa you have to learn? It's right there. 10. What other pKa's are 10? Never review one pKa by itself. Group them with all the 10s. There's a bunch now. We're going to do a quick review of pKa 10 on this video. The original 241s. There was only one of them in well, at the beginning of 241, there was only one of them. What was it? Ammonium. At the end of 241, you forgot because Dr. Whitaker never tested it. What's that called? What functional group? Yes, we should always know what these things are called. Ammonium, thiol. Also at the end of chapter 10, there was a special alcohol. What's that called? Phenol. Not like normal alcohols because of resonance. The O- has extensive resonance. So that is the end of 241. Did we have any other new 10s in 242 until today? I'm not 100% sure myself. That's why I'm asking. Okay. All right. So we know we have a 10 today, and we're putting it here. The whole purpose we're doing this reason we're doing this exercise. Carbonyl number 1, carbonyl number 2. It doesn't really matter what those are. Oh, I don't like circling anymore. Oh. Okay. Alpha to 2 carbonyls. I guess that's the only short form I got. Everything here is pKa. This is not the end of the 10. So why don't you just go to your 241 book and copy the table out by hand and start adding stuff to it that's new. Put it in the right spot. Okay, there we go. End of story.